Sure. Okay, sorry, we're now on slide 4. Okay, sorry about the recording. Okay, and then on the right-hand side, we have a case where we actually have two variables that are common causes, both V and W. And so indeed, controlling for both of these would suffice to eliminate confounding. Now, this is an example of where, we don't necessarily need to adjust for all common causes. It might not be a minimal.
Sorry, can you?
Oh, no. Oh, that's actually not on my computer. Maybe I can. It might be mirrored.
There's a small one here. Probably this is the one. It's really hard to find the cursor on the screen. Okay, yeah.
Oh.
Oh, wow.
Yay. Good job. I'm very impressed at your tech expertise. This is quite a setup. Okay. Okay, so the point is just that, sometimes there are multiple possible sets of covariates that would suffice to eliminate confounding if controlled. But all we're talking about today is a sufficient set. So we might have extra variables in there, but we're not going to worry about that. So today's goal is to kind of be inspired by these ideas from confounding and try to do something similar for selection bias. And so the basic idea is going to be when the causal structure is such that covariate control actually can work to eliminate selection bias, then the set of common causes of the outcome and the selection indicator, not the exposure, the selection indicator will also suffice to do so. Okay. So just as a teaser, this is going to have some interesting implications for missing data. So remember, I said that if we do a complete case analysis, that is, just a form of potential selection bias. There have been a number of pretty influential papers out there arguing that a complete case analysis is unbiased only if the missingness is what's called missing completely at random, which is a very strong assumption that often doesn't hold. So, for example, there is this New England Journal of Medicine paper saying we do not recommend using complete case analysis since it requires the unrealistic assumption that the data are missing completely at random. Another paper in JAMA more recently said complete case analysis requires a far more restrictive assumption. They're comparing it to multiple imputation, that any data point missing is missing completely at random. And so on these grounds, it's sometimes argued that complete case analysis is just inferior to methods like multiple imputation, which make the weaker assumption of missingness at random. So I'm going to be offering a counterpoint, which is not entirely new, but it's kind of motivated by these results, that specifically in the context of estimating average treatment effects, ATEs, I think it actually often makes sense to routinely conduct both a principled, in other words, adjusted complete case analysis, along with some kind of missingness at random assuming method. So complementary, not a substitute, but two complementary approaches. Okay, so what do I mean by selection bias? So here is the pre-Dali version of the oil painting. So the basic idea is we have some general population for which we want our estimate, but we can actually only obtain an estimate among some selected subsample called R equals 1. And so heuristically, we can think of selection bias as kind of comprising two different components. So one is what we might call internal bias. This is bias that arises due to collider stratification because we've conditioned on the selection indicator. We're going to see some examples of this later. But the reason heuristically that we're calling this, that this could be called internal bias, is that it's basically bias that affects such that the estimate we get may not even be unbiased for a causal effect among the selected participants themselves because we have some kind of structural collider or bias. The other potential source of selection bias is what we might call external bias. And so one example of this is effect measure modification, by the selection indicator. So what does that mean? It could be an issue of generalization, basically. So there's something different about the people who are in the selected group. Okay, so just heuristically, for example, we can think about this kind of classic unbiased DAG, right? So we're conditioning on R. R is a collider between A and Y. And so here we actually have potentially both sources of selection bias. We've got, on the one hand, if we condition on R, we've got this unblocked non-causal path between A and Y. So we might think of this as internal bias due to collider stratification. We also have this path between R and Y. And this, basically, you can think of it as here, R might be an effect measure modifier because it shares this common cause V with Y. And so we kind of have both problems here. Okay, so let's get into it. So I'm going to use subscripts to denote counterfactuals, in particular for a contrast in treatments A1 versus A0, with Y being the outcome. And I'm going to assume that our estimand of interest is a conditional average treatment effect called delta Q. And this is defined again for the general population before we've conditioned on R. I'm representing this here as like differences mean differences, but everything here is going to apply regardless of scale. This is just for convenience. Okay, so that's what we want to estimate. What do we actually get? Well, the naive estimand that we actually have access to in the selected sample is going to be called beta Q. And what that basically is just a mean difference between the A1 group and the A0 group, but conditional on only those people with R equals 1. Okay, so remember, our goal is to find a sufficient adjustment set of covariates Q in order to get this naive estimand beta Q to be equal to that in the general population. Okay, so if we knew the full causal structure, we could actually be done pretty soon, right? So we could draw the structure and we could use any number of existing results to find a sufficient set of covariates. So one example is, as a highly general thing, we could use Ilya and Pearl's ID algorithm, which would give us, not only these types of results for selection bias, but indeed for any other type of sort of conditional interventional distribution. There's also other results as well along the lines of selection bias. One approach that Ilya and I worked on recently that tries to kind of codify these ideas of internal versus external bias into graphical rules is based on essentially drawing a swig for the problem. So just as a reminder, this is essentially like a DAG, except that we have split the treatment node into a random component, big A, and a fixed component, little a. So the intuition is just, it's like a DAG, except we're intervening on A. And so if we were to do that, we can actually have kind of two graphical rules, each of which maps onto internal bias and external bias, respectively. And we could try to look for some set of variables Q that would suffice to satisfy both of those. I'm not going to go into this in detail, but like, for example, in this swig here, W would actually work. And so we could then try to collect and adjust for those variables. All right, so that would be great, and the talk would be over. We could just do that. Okay, the problem is often we don't really know the full causal structure. Yeah, please. Yeah. Yeah, no, you're not missing anything. That's exactly right. So it's indexed by A exactly because of situations where it could be affected by A. In this particular swig, this node R would be equal to R of A because it's not affected by A. But you're exactly right. If it were affected by A, we actually would have to depict that, and it would change the conditions we're checking. Okay, so yeah, selection bias is really interesting because unlike confounding, it can manifest in this extremely huge like menagerie of possible structures. So here are just a few. They're very different. There's unbiased things. There's things like this where we just have the selection indicator affected by Y. And so, arguably it may be pretty hard in practice to fully specify the whole structure and how the selection bias is arising. And so that makes it hard to apply some of these existing results. So the question is, can we do something? Can we have rules for which covariates to control, even if we only know something about the causal structure? Maybe we know something about common causes, but we don't know like which of these things we're looking at. All right. So, okay, so again, goal is to find a sufficient adjustment set of covariates, and we're going to do this in a way that doesn't place parametric restrictions and doesn't place restrictions on variable types or link functions either. So, okay, one thing we have to think of at the outset is, selection bias is not the only reason that our naive sample estimand beta Q could be not equal to the general population delta. Namely, what if we have like regular confounding? That would be one reason that these would not be equal. And so for clarity, we're going to think of this conditioning set Q as being composed of two different sets of covariates, C and C. So C are covariates that suffice to eliminate confounding in the general population. So we can think of this as covariates which, if we didn't have this conditioning on selection, we actually had the general population. C is covariates that would suffice to eliminate confounding in that analysis prior to any selection. So for example, we could pick them using, the familiar common cause principle for confounding or something like that. Z are covariates that we're going to condition along with C in order to eliminate selection bias. So we're kind of dealing with confounding with C, and then we've got Z for selection bias. For simplicity in this talk, I'm just going to only show examples where we do not have confounding in the general population. So we're just going to assume that C could be an empty set. Okay, now another thing that's interesting about selection bias that's different from confounding is we need some ground rules about which variables we are willing to consider adjusting for. So in particular, we don't want to adjust for variables that are going to cause other types of bias, even as they eliminate selection bias. So for example, we don't want to condition variables that are affected by the outcome or affected by the selection indicator. That would basically give us something that's not interpretable as the causal effect we want. We also don't want to condition on mediators or variables that are affected by mediators, because that would block part of the total effect. And so that would be not helpful. So, okay, so now this is kind of the main result, which basically says if there exists a sufficient adjustment set given the causal structure, which again, we may not know, but if a sufficient set exists, then the set Z of all common causes of the selection indicator and the outcome, excluding the exposure and variables affected by the exposure, that is also a sufficient adjustment set. So why do we have this clause here? This is basically dealing with this problem of we do not want to condition on variables that will cause their own problems. Okay, so here are a few examples. These are three cases where a sufficient set does exist. And in each of these cases, I've boxed V because it is exactly the set V, right? The common causes of R and Y that are not affected by A. And so in each of these cases, indeed, controlling for V would suffice to eliminate selection bias. And kind of the thing that's interesting, right, is we don't actually have to know exactly which of these structures we're in to apply that result. We would need to ask ourselves simply, what are the variables that cause both R and Y? And it doesn't really matter which exactly of these we have. Okay, but now we have the caveat, right? So when will a sufficient set exist? So unlike for confounding, some causal structures, unfortunately, are hopeless for covariate adjustment with selection bias. There is not a sufficient adjustment set in the way I've described. And so it turns out that there's actually two categories where this would happen. So first one is what we call type D insufficiency. And so this is where either the outcome itself affects selection or selection affects the outcome. And the other possibility is that we have some mediator between A and Y, and either the selection indicator actually is that mediator, so A affects R affects Y, or the selection indicator is affected by that mediator. Okay, so this is kind of nice because, I mean, it's bad news that there are these cases where we can't use covariate adjustment, but the good news is at least we can try to reason, hopefully on substantive grounds, about when these things might or might happen. Is it plausible that the outcome would itself affects the selection indicator? Is it plausible that, selection is a mediator, for example? So here are 3 examples where we don't have a sufficient adjustment set. And so here, again, I've boxed V when it is the set of common causes that are not affected by A, but it's not going to suffice in these examples. So in these first 2, we've got a directed path from Y to R in both cases. And here we've got a mediator V, and R is affected by that mediator. And so here in these cases, we are not going to find any covariates whose adjustment will suffice. Okay, so what if we might not have controlled for a sufficient set? So maybe we didn't actually measure all the common causes. Some of them aren't available in our data set, or we have limited substantive knowledge, and so we can't think of them all. So I think arguably it makes sense to try to follow up this kind of approach with some sensitivity analyses, just as we might do for confounding, right? We might try to control for confounding as best we can, and then we might do sensitivity analyses to query sort of how much the results could change if we've missed some of the confounders. And so we could conduct sensitivity analyses that are very closely analogous to those for confounding. Some of these are work of Louisa Smith and Tyler Vanderweel, and there's also another approach that I may touch on at the end if we have time. So going back to complete case analysis. So remember, if the data are missing completely at random, this guarantees that complete case analysis will be unbiased regardless of the estimand or the analysis model. And again, influential papers say this is actually necessary. Well, let's think about what we just said in terms of selection bias. So what we just saw is there are actually many settings where complete case analysis that is adjusted for a sufficient set of covariates, that's a key clause, will be unbiased. And in fact, this can be the case even when the data are missing at random, or importantly, even when they're missing not at random. So that latter thing is important, right? Because there are cases where complete case analysis that's adjusted appropriately will work even when we do not have a guarantee that methods like multiple imputation, which assumes missing at random, will work. So again, complementary approaches rather than one being better than the other. This is not new. Yeah, please.
I don't know this literature that well, but I guess I would have assumed that complete case analysis meant unadjusted, like just the naive complete case analysis. Is that what these claims are saying?
It's possible. I mean, it's interesting because some of these are referring to kind of observational data settings where we're probably adjusting at least for confounders. And I do think it's kind of an interesting thing to ponder is like, to what extent is the set of of confounders that we adjust for routinely in observational studies some of them might actually be the common causes of selection and why as well. So, but I think you're absolutely right. I mean, it's interesting, right? Like in an RCT, we might be on actually worse footing in terms of adjusting for common causes of R and Y, because we might not adjust for anything. But yeah, certainly if we have an unadjusted complete case, we have a much lesser chance of having it be unbiased for selection bias. Yeah, so and then this is not this is not new information. I mean, I think as usual, Nan Laird said it way back when. So she has this beautiful paper in 1988 that does all kinds of things, classic Nan Laird. And in there she has this little sentence, complete case analyses may yield valid estimates of certain parameters, even with non-ignorable response, which is another way of saying missing, not at random. And so, actually this is pretty intuitive, right? We can all think of examples, like one is just logistic regression for case control sampling. So again, case control sampling is when we sample based on the outcome. And we use logistic regression because it will work even under that form of selection. Now this, and so that's, not missing at random. Now this is a very specific case that is specific to one link function. But the point is these concepts around sufficient adjustment sets work regardless of the estimand or the link function. So it kind of broadens our view of, what types of structures might we be able to handle with a complete case analysis. In simulations, we found that often, even when a sufficient set actually does not exist, still adjusting for the common causes of R and Y in complete case analysis actually may still substantially outperform multiple imputation in missing not at random settings. So it's sort of like adjusting for the common causes might help the complete case analysis do better. It might even do better than missing at random assuming methods. Now, not claiming that this holds always, but it does hold in a number of cases. So that's interesting. And so, I think basically it makes sense to, at least by default, conduct both types of analyses. Try to conduct a sufficiently adjusted complete case analysis, try to conduct something like multiple imputation or IPW, and compare the results, and don't necessarily assume that, the results of that if there's a difference, it inculcates the complete case analysis. It could be the multiple imputation that's off. Okay, so what we've seen so far is, I think in practice, we want to first think about whether a sufficient set is plausibly going to exist for our setting, right? So if we think that the outcome itself affects selection or vice versa, we're not going to be able to do this. This isn't going to work. Or if we think that selection is a mediator or is affected by one, again, not going to work. Could still help the complete case analysis to adjust, but it's not necessarily going to be unbiased. And then, we want to actually make sure we try to collect and adjust for common causes of Y and R. And the interesting thing here that's also a little bit different from confounding is these variables might not be baseline variables. They might not be variables that are occurring temporally before the exposure. In observational studies, we're used to collecting, a broad swath of confounders measured at baseline, and that's fine because a confounder is not going to be a variable that happens temporally after the exposure. Not so with common causes of selection and Y. They could be variables that happen after the exposure. And so, arguably, we want to think about this a little bit during study design, right? And try to think about, are there variables I need to collect that are not pre-exposure temporally? And again, even if a sufficient set doesn't exist, adjusting for common causes does often improve selection bias compared to a naive complete case analysis. Okay, so I want to pause there, and yeah, let's see if there are questions at that point, and we can do some sensitivity analysis if we have time. Yeah.
Some people who believe in regression
Yeah, that's a great question. Yeah, love that. So, so basically, if you're only concerned with, so this also gets to this caveat about what happens if selection is affected by exposure, but let's think of a simple setting where it's not. So if we're in a case where selection is not affected by the exposure, then in fact, we would only need this first condition here to hold. So in other words, no backdoor paths in the swag between YA and A, conditional on R. So the intuition is, this is basically saying we need to not have internal bias with respect to the selected group, but we don't care if there's some path between Y and R, because that would essentially be like a generalization problem, which we're not worried about in the setting that you described. Yeah.
For those
yeah, great question. So Oh, absolutely. Thank you, Beth. I will absolutely do that. So I think that, yeah, this question was in the chat, so I won't repeat it. Yeah, so this is basically saying, well, we don't necessarily have the general population distribution of V or C, so isn't that a problem? So that would be a problem if our estimand of interest were not a conditional ATE, but rather an ATE that marginalizes over those variables. So indeed, there are some cases where, if we don't have V or C measured in the general population, we could get a conditional ATE, but we could not get an ATE marginalized over their distribution. There's also other cases where, we actually could marginalize, like an example would be if we've got a mediator between A and Y and that mediator affects selection, well, we can't do a conditional ATE, so we can't condition on a mediator. We're going to not get a total effect, but we could marginalize over it. Okay. Yeah. Yeah, I mean, I would actually defer to Ilya on this, but I think it would probably be very hard with a large graph. Is that true, Ilya? Oh, I guess.
I don't think graphs are.
Okay.
Computationally hard.
Yeah, okay, well, actually, first, let me summarize the question. Yeah, so the question was, suppose we know the full causal structure and we want to do an exhaustive search to look for sufficient sets. Is that basically computationally infeasible? So I mean, I imagine it depends on, how complicated the structure is.
To find a case.
No, this is not. If you know the graph exactly, it's not a hard problem. So this is like, okay, so let me just ask you a single A, single Y. Like, what is your query exactly? Causal effect and how many outcomes come from G? And you're doing adjustment. So I think like I'm asking because it matters. I think like if I have a single A and a single Y, I don't think it's very hard. So we can talk offline about it. If it's multiple A's, I think it's harder. But not so much.
Okay, so to summarize for the Zoom crowd, the answer was we can chat offline. The answer is going to depend on how many exposures, how many outcomes you have, and those types of details. Yeah. Mhm. Yeah, that's a great question. So that starts to get into kind of general missing data problems, right? Where it's like maybe we're just interested in one variable as our as a component of our estimand. So there's a really cool paper. There's several cool papers, but one is Razier by Razier, Navi, Ilya, and co. In 2022. That's a preprint that kind of goes into these considerations. But I mean, basically, what you can do is have kind of an augmented version of the graph that has missingness indicators for each individual variable, and you can then kind of restrict it to the variables that are involved in the estimand you want. So that could be just one variable, for instance, and you can then kind of use similar principles of deseparation to reason about what needs to be adjusted. Yes, I'm sorry. Okay, yeah, so the question there was, what if instead of an ATE, you have some other type of estimand that you're interested in? Maybe it's just a prevalence or a mean of one particular variable.
So if you're interested.
Yeah. Well, so for the first question, can we just get the conditional average treatment effect conditional only on C? well, this depends on whether C is measured among only the R equals 1 group or among everyone. If it's measured among everyone, then if we were not conditioning on R, then we could, right? That would just be sort of a plain vanilla confounding adjustment. But it could be that C is only measured among the R equals 1 group, and that will be fine if you only want a conditional average treatment effect. In other words, that conditions on, R, C, and Z wouldn't work if you wanted to marginalize over C. Because indeed, yeah, if you wanted to marginalize over C or Z, you would need to actually measure that variable in the general population or make additional assumptions. Cool. Okay, I'm going to say a little bit about sensitivity analyses, more of a teaser than a full treatment, but it'll be fun to connect the ideas. Okay, so the second part is, addressing this issue of, well, what if we actually haven't adjusted for all the common causes of R and Y? What then? Can we do a sensitivity analysis to see how much the results might change? So just as a kind of running example, we might consider a longitudinal RCT, which looked at the effect of receiving financial incentives to stop smoking on smoking cessation. And this study had pretty good retention of 86% in the first 6 months of follow-up. And it was pretty comparable between arms. But, they basically did a complete case analysis, which estimated a relatively small beneficial effect, so a risk difference of 0.11. And so we might ask, this is kind of a small effect. Could this be entirely due to missing data? So the idea here is to kind of following on the previous work, to do sensitivity analyses in a way that accommodates many forms of missing at random or even missing not at random, and that doesn't require the missing data mechanism to be fully known a priori. These ideas are heavily indebted to both the e-value approach for confounding and analogs for selection bias that I mentioned earlier. And the goal here is just, pretty simply to accommodate some potential additional information that seems plausible in context of missing data. So in particular, the proportion of missing data that we have, and then potentially also in some contexts, we might believe that the treatment is not going to be detrimental on average, even for participants who are not retained, by which I mean not in the selected analysis. So let's think about the smoking example. We might be willing to believe that even people who drop out of the study are unlikely on average to have a detrimental effect of financial incentives. We might say it's just not that plausible that, for these people, giving them financial incentives would make them smoke more. Okay, so we can kind of incorporate that type of a priori belief into these sensitivity analyses. Another goal is to subsume certain methods of doing worst case imputation. So what does that mean? People will often say, okay, well, I've got this data set with missing data. Let me try to fill in the missing values, not using something like multiple imputation, but rather plugging in kind of the most unfavorable values I can think of. So let me plug in like the worst case outcome for everyone who dropped out and was in the treatment arm, for example, and vice versa. So this is kind of a one-step approach that will subsume some of those methods that involve plugging in individual values. Okay, so setting is similar. I'm suppressing conditioning on covariates, but you could do that throughout. So we again have delta as our general population estimand, and we've got beta as our naive sample estimand. And so our goal is basically to bound this general population effect delta using the naive sample estimand beta, the probability of retention, so the 1 minus the proportion of missing data, as well as two other quantities, which I'm going to discuss more. One is the population ATE, in other words, the true causal effect among participants who are retained in analysis. And the other is the true causal ATE among non-retained participants. We'll see how each of these gets dealt with. Okay, so we already talked about internal and external bias. So basically the idea is super simple. So if we're working with something with an ATE that's on the difference scale, then we can just decompose the general population ATE into components from the R equals 1 group and another component from the R equals 0 group. Okay, it's just a weighted average. Now, we've got two things to deal with here. So let's look at this one first. This is the true causal effect among the non-retained participants. So in this approach, we actually treat this as a sensitivity parameter. We are not going to try to estimate this component or bound it. So we have a couple of possibilities. One is we can be as conservative as possible. Let's say we're working on the risk difference scale. We can set it to -1, right? So that's similar to worst case imputation, where we say, let's just plug in the worst possible value that we can think of. And this is actually similar to what's implicitly done in a number of other sensitivity analyses for selection bias, making this maximally conservative assumption. Less conservatively, though, the point of having this as a sensitivity parameter is that we could choose to set it to something else, right? We could choose 0 if we think it's unlikely that the treatment is detrimental on average, even among the non-retained participants. Okay, what about this other component? Well, this one is interesting because we actually have some information about the retained participants, right? We measure something about them, but it could be subject to internal bias. And so, I won't get into the details here, but basically this one can actually be bounded using some relatively simple proportions from the sample. This is the P terms, as well as something called B, which is a bias factor. And basically what B is it tells us something about the strength of relationship between unmeasured variables and the selection indicator, as well as the outcome Y. And it basically takes the form of, it has two sensitivity parameters in it. One talks about the strength of association between U and Y, and one talks about the association between U and R. I'm sorry, between A and U conditional on R equals 1. So I won't get into the details here. We're running out of time, but essentially you could also do something that's similar to the E value for confounding, where you solve for the severity of bias that would be required to explain away your estimate, for instance. So for example, if we did this type of approach with the smoking example, one analysis we might do is to indeed assume that the incentives are not detrimental on average, even among the non-retained participants. So thus setting the sensitivity parameter to 0. And if we do that, we would basically find that the strength of association that unmeasured variables would have to have with treatment arm or with smoking among those who are retained would need to be at least 3 on the risk ratio scale. That could potentially explain away the point estimate. And so, this is interesting because although we don't know a whole lot about the reasons for dropout in this study, we might say that seems relatively strong, especially given that retention seemed pretty comparable between treatment arms. And so if we thought that was the case, this might seem relatively robust to bias due to missing data. So we are getting up on time, so I'm going to leave us there. So here's a slide with, thank you to my collaborators. Slide deck is online, and then some links to papers as well. So we probably have time for like 1 or 2 more questions. Okay, there's one in the chat, which I'm going to read out loud on the first try this time. Okay, it says, okay, the question is thank you. So thank you, good questions.
Well, while people are thinking about questions, let's thank Maya.
Well, it's tricky, right? So you wouldn't want to control for, you could control for it if it's not affected by the exposure. Okay, I'm so sorry. Yes, the question was, I'm gonna get this right eventually. We need to keep doing questions till I get it right on the first try. So the question was, yeah, so if you have a variable that is a common cause of R and Y, but happens temporally after the exposure, should you control for that? So you wouldn't want to control for it if it's potentially affected by the exposure. It could potentially then cause its own forms of bias. If it's not, then you would want to still try to adjust for it and control for it if it is a common cause. So yeah, you could do that through covariate adjustment. Now you could do something similar with a weighting approach, but it would be at least safe to adjust for it.
in the multiple imputation complete case analysis comparison, are you sort of multiply imputing and then adjusting in the same way that you know, that typically people do multiple imputation followed by a regression adjustment. So I couldn't tell from the slide the comparison between adjusted complete case analysis and sort of naive multiple imputation. Adjusted complete.
Yeah, great. So the question was kind of when comparing complete case analysis to multiple imputation, are we talking about naive multiple imputation where you know, we impute, but then we don't adjust the outcome model and analysis, or are we talking about maybe some kind of imputation followed by adjustment? So we looked at both. So standard practice is to kind of impute, assume that deals with the missing data problem. Maybe we adjust for confounders, but we typically do not think of adjusting for selection bias sufficient set. So we did both. We did also do multiple imputation where we additionally adjust for the sufficient set. And that did typically perform better in situations where a sufficient set existed, but missingness at random was violated. So it kind of helped with you know, getting MI to work, even in certain situations where missingness at random is violated. Now, sometimes interestingly, even that type of adjusted imputation sometimes still did worse than complete case analysis that was adjusted. And I think some of that has to do with it can be slow to achieve its asymptotics. And so sometimes it was okay asymptotically, but it took, you know, a relatively huge sample size. So I do think, again, doing both is probably useful. And there were cases too where I think the imputation itself kind of introduces bias when you have missing not at random, such that even that adjusted estimator does worse asymptotically. We've got one in the chat. Thank you. Okay. Great. Well, I think we are at time, so I think we can go ahead and wrap up. But thank you all for the great questions and the engagement.
Thank you.